So let's talk about a new concept that we haven't before, and that's something called noise margins. So in a given integrated circuit chip, like we said, typically we always want values that we call logical 1 and logical 0. And logical 1 is a value of VDD, logical 0 is ground. However, as you notice from the previous foil, if you have a value that's not quite input of ground or VDD, you can get an output from your gate, logic gate, that could be not quite exactly either a 1 or a 0 or a VDD or ground. Now, as long as we're close to VDD or ground, the closer we are, the better. But as long as we're pretty close, we can still say logically we know something that's, let's say, 90% or 95% of VDD we can call a logic 1, and similarly, 10% of, down near ground, 10% of VDD, or 5% of VDD, we can say, oh, that's close to ground. So if we're talking about noise margins, what we're talking about is if we look at the input, so in this particular case, let's say we have an inverter driving another inverter. We want that first inverter, we want its output to be pretty close to either VDD or ground. So if we define a range near the top, near VDD, that as long as we're greater than this voltage, we can say, yes, this is outputting a 1, and as long as it's low enough within a certain range, we can say this, we'll define this as a 0. So we have a large, this range near the top and bottom. If it's somewhere in between, it might be switching on its way toward a 1 or a 0, and so we might be a little bit unclear as to whether that output is supposed to be a 1 or a 0. So we have, for output characteristics, we can say there's a certain range near the top and bottom that we'll define as a logical high or logical low. Likewise, if we have the input to a transistor or to an inverter is close to a 1 or close to a 0, defining whether it's a 1 or a 0, we can define a certain range that we say, as long as it's higher than this value, we'll say that the input is a 1, and lower than this value, the input is a 0. The thing that we would like is we want to make sure that our output of our first inverter is in that range that matches the input range that we've said we can determine this is a 1. So if we have that first inverter is outputting a value that's in the hashed range of a 1 or a 0, and that range of the output is a smaller range than what our receiver is saying, as long as I receive something in that range that's the hashed range of the inverter of the receiver, then it knows, yes, this is a 1. So we want our outputs to have a smaller range than the range that we allow for the inputs, and as long as that's true, then we'll always get a value that we know going from one output to the next input. And that indeterminate range, if you think back to the transfer characteristic that we had of the previous foil, as long as you're not in that really steep range where things are switching between 1 and 0, if you're in more of the flat tail range of we're pretty close to VCC or VSS, we should be good. But if for some reason there's some sort of noise on our input signal causing us to get into this indeterminate middle region, then that causes problems for us, and so we want to try and avoid that type of noise. So on the previous foil, we had shown that there were certain voltage levels that we wanted to be greater than or less than in order to make sure that we could determine whether we were at a high logic value or low logic value. And the question is, how do we determine what those logic levels are in order to say, oh, we're within our noise margin of determining whether something is a 1 or a 0. In effect, if we look at, so if we want to maximize what our noise margin is, if we look at the graph below here, we can see as long as we're not in that really fast high slope region in the center of the curve here, if we're, like I said in the previous foil, if we're in the tail region on the left or on the right, then we should be in a good region for determining that yes, we're at a 1 or a 0. So hence we want to select the voltage logic levels in this particular case at what we call the unity gain point for this DC transfer characteristic that we have graphed here. And these unity gain points are where you can see that there's a slope of -1 at 2 different spots on this curve. One is near where the tail at the top left is tailing off toward VDD. You can see that as that, once we get past a slope of -1 there, it starts going to the right, it starts going really steep really fast, and then when we hit slope of -1 for the tail on the right hand side, it flattens off again. So so that's typically in industry, when you measure that V out to V in curve, where the slope hits 1 is where we say these are the points that if your Vn low and Vn high, in between these 2 points is bad and you don't want to be there. And so if you see noise that hits that range of voltage, you say that's a violation. And similarly for your V out, you want the V out, VOL and VOH to be between those 2 points that you can see measured on that graph. So we'll talk about this more when we get into sources of noise and how to reduce sources of noise, how to measure noise, etc. in the future. Much of the time up until now, when we've been talking about the input and output of a logic gate, we've been talking about the DC analysis. So if you have a certain voltage in, here's what the voltage out is. In reality, most of the time when we're actually sending signals through a cone of logic, multiple logic stages, we are talking about the transient response. So it's if we change the value of Vn, so transient analysis tells us what is V out as a function of time if we change the input over a function of time. So this requires solving pretty complex differential equations if you're trying to do it purely theoretical, and that's why usually we don't wind up doing that often. We use the circuit simulators, but we can make it a little bit easier. Usually what we'll take is take the input and usually consider it to be either a step function, like pure changing it from 1 to 0 or 0 to 1 at an instant in time, or more like a ramp. The ramp is more often used where we consider it to be going from 0 to VDD at a certain rate. Getting there in a certain period of time at a constant rate. And usually something like a ramp is good enough to get us pretty close to the right response on the output. So let's go through an example here. If we have an inverter and we actually put in a step response. So if we put in a pure step function at the input to an inverter, what do we get? What does it look like at the output to the inverter? So our Vn is, we have a value over time, u of t minus t0, a function of time, times VDD. So if u is 0, we have 0, and as it switches to a value of 1, we get VDD. So if Vout for time less than t0 is VDD, so if our input at time less than 0 is 0, our output at time less than 0 is going to be VDD. And then voltage Vout sub t as a function of time is going to be the current through the NMOS device as a function of time divided by C load. And inverse of that, so negative of the current divided by C load. And so our voltage changes over time based on the current through the NMOS device and the total load capacitance that that current needs to switch between VDD and ground. So the current equations, when time is less than t0, you have 0 current. As soon as the input switches to VDD, then for a period of time we have the current equation is beta over 2 VDD minus VT squared. So that's while the NMOS is in saturation. That's the current that we're going to get. And then as the voltage gets lowered, gets pulled down from VDD, eventually the NMOS device goes into the linear region, and so then we get the linear region equation while we're in the linear region. So the current will be reducing as Vout is going down, and so it's going to reduce at a slower rate as time goes on. So if you look at how the step function looks in terms of Vn versus Vout, the curve winds up looking like the curve in the lower right corner here. We have at time equals t0, Vn goes from 0 to VDD. Vout starts at VDD, and as soon as the NMOS turns on, you start getting current that is, since VDD minus VT squared is a constant value, it's not dependent on Vout, you're going to get some constant current value for a while, and that's why you see the curve at the beginning is more of a linear curve, because it's based on the value of current and the value of C load is the slope there. Then once we start going into the linear region of the transistor, that starts tailing off and the slope starts getting more flat. So on the previous foil we talked about what happened when the input delay switches as a step function, but in reality your input is always driven by the output of a previous gate. And so as you saw, the output of a gate has a certain slope to it, and typically will also start tailing off, and the slope will start degrading as it gets closer to its endpoint. So here we're showing if we have an inverter, for example, that has an input waveform that's kind of a square wave, but where the rising edge has a slope to it and then also starts tailing off, and then when you start switching back to low, it will have a slope to it and again start tailing off as it reaches ground. Let's talk about how we define the delay from the input switching to the output switching, and also where we measure what we consider to be the input switching, like the start of input switching or the time that we declare the input to have switched, to the time we declare the output to have switched. So one definition is what's called rising propagation delay. This is T sub PDR, so PD for propagation delay and R for rising. This time is the maximum amount of time that it takes from when the input switches to the rising output switching. And what we define as the switch, the point at which they're switching, is when either the input or output crosses 50% of VDD, so VDD over 2. So in this case, if you look at the right hand side of the waveform where the input is switching from high to low, when it gets from VDD to half VDD, we start measuring time. The output initially starts low, and around the time that it hits the 50% point, the output crosses its that switch point that we talked about several foils ago, where as the input gets higher than 50% of VDD, the output now sees, oh, I should be switching from high to low, or from, in this case, low to high. And so the output starts switching, and once it reaches 50% on its way up to VCC, we consider, okay, that's the point at which we declare it to have switched over to the other logic value. And so that time period from 50% to 50% is our rising propagation delay. And of course, our falling propagation delay is on the other side when input is switching from low to high, output is switching from high to low. The output is falling, so it's the falling propagation delay, and you measure from the 50% input point to the 50% output point, and that amount of time is your falling propagation delay. Then we have what's also called an average propagation delay. Sometimes if you just want to give one metric for a given gate, rather than rising versus falling, you average the two. So add the rising propagation delay to the falling propagation delay, divide by 2, and get your average, and that's your average propagation delay. Now keep in mind, I've been talking about the output, so the rising and falling depends on the output rising or falling. And I'm not saying whether the input is rising or falling, because sometimes you'll have an inverting gate like an inverter where the input rises when the output falls. Other times the gate will be like a pass gate where it's non-inverting, and so the output will fall when the input falls. And so the definition of rising versus falling is always talking about the output is rising or falling. And the other thing to keep in mind is here for propagation delay, we're talking about the maximum amount of time it takes for that to happen. And the reason is, in some cases, gates will have varying amounts of time for rising and falling delay, depending on if you have, in particular, multiple input gates. If the inputs are rising or falling at the same time, you will get a different delay than if only one of them is rising or falling. And so there can be a difference between the maximum time and minimum time. Next, we also have what is the amount of time that the output takes to actually fall. So this is dependent on the slope of the output curve. So for rise time, by convention, we tend to measure the rise time from the time the output first crosses 20% on its way to 100% of VDD to the time it takes to get to 80%. And the reason why we don't do 0 to 100 is because as these waveforms tail off, the 100% point becomes a really, really long out there time. Whereas the 20 to 80% point tends to be a little bit more consistent and measurable, and consistent from gate to gate as far as trying to measure that value. And of course, fall time is the amount of time it takes for a falling waveform to fall from 80% of VDD to 20% of VDD. Here's a couple additional delay definitions, and this is mainly what is called the rising contamination delay and falling contamination delay. Previously we had talked about the propagation delay. In this case, rising and falling means the same thing as last time. It's the amount of time from the input changing, either rising or falling, for the rising contamination delay, minimum time from input crossing 50% to the rising output crossing 50%. The difference between contamination delay and propagation delay is the propagation delay was the maximum amount of time from the input to the output crossing 50%. Contamination delay is the minimum amount of time from the input to the output crossing 50%. So in this case, if you have a difference in delay time for varying different inputs switching, whatever the minimum time is the contamination delay. The maximum amount of time is the propagation delay. And then of course the average contamination delay is just averaging the rising and falling contamination delay. So now that we know what propagation time is, if we, in effect, we've said before, we don't really want to go about solving these complex differential equations by hand. Since our input is a waveform that's changing time not as an exact slope or even a step wave function, and it's got a variable value as it's changing time, and the output changes over time with a variable value. It makes it really hard to solve by hand. Generally, we'll put together a SPICE simulation and simulate it in order to get an accurate propagation delay from input to output. But even the SPICE simulations do take time to put the circuit together, add the waveforms in order to actually simulate it, and also doing simulations sometimes can hide a little bit of insight into exactly how the circuits are working. So there might be other ways that we can look at this to try and get a reasonable estimation for what our delay is, but also get some insight into how it's working. So one way that we can get some insight into how the circuit is working without necessarily doing entirely accurate equations for response times or doing simulations is if we would like to be able to easily estimate what our delays might be. It's not going to be as accurate as simulation, but it's a lot easier to ask what-if equations if you start changing values of either capacitance or transistor sizes, etc. So the thing to note when we were looking at our output response in the previous foils, if we put a step response into the input, usually the output of the stage that we're looking at, like an inverter, looks pretty close to a first order RC response with basically a decaying exponential. So we start off looking a little bit like we're got a constant slope, and then it starts decaying later. And so typically one of the ways that we can estimate delay is we use an RC delay model to estimate our delay. Our capacitance C is going to equal the total capacitance on the output node that we're driving, and then we have to figure out what value of R to use. And so we want to use an effective resistance, and so we're modeling the transistor as if it has an effective resistance of R, so that way our propagation delay for either rising or falling is going to be equal to this RC, or at least proportional to an RC value. And so we're going to try and characterize the transistors by finding their effective R value. And this effective R value will depend on the average current going through the transistor as the gate is switching from, as the output of the gate is switching from high to low or low to high. So finding out the effective resistance, we could use the Shockley models that we've used in previous courses, where we calculate what's the maybe small signal resistance or something of a or even large signal resistance of a transistors. They typically, for modern transistors, they're not accurate enough, and they can be too complicated to try and figure out for hand analysis. So typically, instead of a Shockley model, we'll, as I said in the previous slide, treat the transistor as if it's a resistor. Replace the IDS as a function of VDS and VGS with just an effective resistance, where we say the effective resistance is if we use IDS equals VDS divided by R, then we can say our effective resistance is your IDS over VDS, and the average of that value averaged across the switching of VDS from VDD to 0. Now, this model is too inaccurate to be able to predict the current at any given time along the curve, but it's good enough to try and predict, something like just what is the propagation delay, for example, even though we won't be able to know, okay, if I wait until 90% and to get to the 90% point of switching, or the 95%, you're not going to be accurate, but to go 50 to 50 gives us at least a reasonable approximation. So if we want to use a RC delay model, one way we could do this is we can choose an equivalent circuit for a MOS transistor. One of the choices for that would be, let's treat it as if it's an ideal switch, but add capacitance to it at the gate, the source, and drain, and also add an on resistance. So when the switch is closed and it's on and conducting, you have a resistance there instead of a pure switch. If the size of the transistor is, if we're using the unit type of notation, where we have a given for k equals 1, you have a certain width, and based on the minimum length of a transistor, we've talked about the unit sizing for NMOS and PMOS transistors before in integrated circuits. Then the capacitance is proportional to the width. In other words, as k goes up and you get wider, the capacitance goes up as well. However, resistance is inversely proportional to width. So as the device gets wider, k gets larger, the resistance goes down. And the other thing to keep in mind is that in NMOS, we'll have a resistance and capacitance that is proportional to k, and a PMOS will have a resistance that is that is 2 times the NMOS, because the PMOS is has mobility that's about half of the NMOS. So its resistance is larger than PMOS. The capacitance is going to be the same, because for similar width they both have the same capacitance, but the PMOS will have a higher resistance. Just to give you a few example values of capacitance and resistance, if you say our capacitance C is equal to our gate capacitance, source capacitance, and drain capacitance per unit width, in the 0.6 micron process, each of these values is approximately on the order of 2 femtofarads per micron of gate width. And then as scaling has occurred on process generations from about the 0.6 microns is 600 nanometers. Going from 600 nanometers down to 65 nanometers, that capacitance per micron has been declining for various reasons of scaling to about 1 femtofarad per micron. Just as some examples of real life numbers. For resistance, it's approximately 10 kiloohm per micron in the 0.6 micron process, so whatever width you have, take that number of microns, and then it improves with shorter channel lengths, and so as we go from the 600 nanometer down to 65 nanometer, going down to 1.25 kiloohm microns. And so for our unit transistors, we may refer to the minimum contacted devices as the 4/2 lambda. It doesn't really matter whether you go by units or whether you go by actual microns, as long as you stay consistent with how you're doing your measurements. So just make sure to know what your process is, what your device sizes are, in order to determine what the capacitance and resistance values are. Let's do an example calculation here, estimating the delay of a fan-out 1 inverter. So we have a minimum size inverter with PMOS twice the size of NMOS, driving another minimum size inverter with PMOS twice the size of NMOS. Calculate the delay in terms of, if we have a value of R and a value of C, let's not actually put in an actual number for R and C, but just do the delay in terms of time relative to a function of RC. I'll give you a second to try and calculate this yourself, and then we'll go through it. So if we have this, if we now replace every transistor with that estimated model that we had, where we have now a switch with capacitance and resistance for each of the transistors, then we wind up with something that looks like this. So we now have each of, for the first transistor there, or first set of transistors, the R's are replaced, or the transistors are replaced with a value of R. Since the PMOS is twice the size of the NMOS but half the strength, both the PMOS and NMOS have a value of R. And if you go back a couple slides, you'll see that that would be true. With a PMOS twice the size, should have the same R value as the NMOS. Now for the capacitance values, the NMOS has in the source and the drain a value of C, and the PMOS has a value of 2C for each of the transistors in the drain of the first set of transistors. Then of course those are going to drive the gate of the second set of transistors. The capacitance of the PMOS gate of the receiver inverter is 2C, and the capacitance of the NMOS gate is 1C. So when we look at the overall circuit here, we're left with, if we're driving a 0, for example, we're left with a single R driving two values of 2C and two values of 1C. Overall capacitance value there is 6C. So our time constant is a factor of R times 6C. So that gives us something that we don't have to actually go simulate this, and we don't have to do some complex equations, but we can get a relatively quick time constant of 6RC. The question is, how close does that estimation that we just did come to the actual simulations or actual behavior? So if we were to look at the different models, if we put this device, or put this switching two inverter circuit into SPICE, we would get the result of the curve in black there. If instead we modeled it as a Shockley type model, we would come out with the curve in blue, which fits pretty well to the curve in black. It's a little bit off. And then if we looked at our model, which is the curve that's the dashed black curve, BRC model, we would see that when we get to the end of the curve, more in the right hand side, we're off by the SPICE curve a decent amount. We see more error there at least. But in the beginning part of the curve, when we're going from VCC to 1/2 VCC, you can see that the delay, if we're just looking at the delay to the 50% crossing point, is actually even better or closer to the SPICE results than the Shockley curve was. So as I said previously, if we're just looking at the 50 to 50% time at the beginning part of the switching, this is not too bad of a model to use for estimating our delays.